Okay. So this session is being recorded, and we will share this recording at the end of session. So you do not have to have a distraction of taking notes. If you are you have to take a notes or you have to do something, you can just quickly take a screenshot and put it somewhere. But it's not required at all because I'll be sharing this presentation with all of you, as well as the video will be shared to you. Okay. Some of us would love to, it's a good point because some of us love to blog about it at later point of time. In last few sessions, people have written really nice about this session. They have summarized in their blogs. So, and if you're into technology, blogging is a good habit of taking notes so that it becomes easier. So you might love to take notes and then blog about it. But I would strongly recommend that whenever you have to take a note, you just take a screenshot and put it in a doc. All right. I will anyway be sharing the video as well as or the presentation with you. All right. This session is being recorded. So Manikandan is a technology profession. Hi Manikandan, welcome to the session. He's having 15 years of experience in software design and development and has a strong desire to shift into exciting analytics. Great choice, right? Okay. So Ashish Tyagi has got a question. What type of role big data in computer field? I need only small description. Okay. So the question might be small, Akash, but the answer is a little longer. And I would love to answer this question. Once you have gone through the big data and Hadoop session, you will yourself be able to answer this question. Okay. All right. Hi, Anand. Anand Gadikeri is having 7 years of experience in Java J2E and want to know about from this session a basic understanding of Hadoop and configuration, some example. Yeah, you will get that. Yeah, you'll get that. Nothing to worry, Anand. Okay, so Manikanda's question to all of us is that is anybody working in data mining in Hadoop, like using Mahat etc? So Manikandan, I had been using Mahat for quite some time, and now we are experimenting with GraphLab and similar tools. So you could ask me a question if you have after the session is specific to Mahat. All right. Hi Bharat. Bharat is a software developer and he would likes to learn new technologies and has 4 years of experience in .NET. Welcome Bharat. Welcome to the session. So Manikandan's point is that he wants to collaborate with folks here to work on some project on big data mining, machine learning using Hadoop and Mahat. Great. So Manikandan, what we will do is we'll start a thread on our meetup group itself in which you can ask this question and then everybody will be able to answer and then connect. All right? And I'll also try to help from my side. Great. Hi Kamalkar. Kamalkar is having 3 years of experience and working in C++. As of now, he is a freelancer and he would get into analytics. Great choice, Kamalkar. And okay, all right. So great. So anybody else? Okay, hi. So we have Arvind Kamath, and Arvind Kamath has been in IT industry for more than 8 years and has been working on Java for last 8 years and have heard a lot about big data and Hadoop and looking forward to the new technology. Great, Arvind. Good choice. So does anybody have? So feel free to give your brief introduction. The only problem is that because in GoToWebinar, the questions are questions of one person is not visible to anybody. I'll have to read it out. All right. So please feel free to introduce yourself. It will be a great one. So I'm behaving more like a radio jockey here, reading out things. And hi, hi, Ankali Vara Prasad. Yeah. So hi, Prasad. Please introduce yourself. It'll be great. All right. So Prasad is 8 years into middleware administrations. Great. Anybody else? Okay. So Ashish Tyagi is works in web development. Great, great. We have Prasanna. Prasanna has 13 years of experience in Java and SQL and interested about Hadoop. Great, Prasanna. We have great team over here. And okay, okay, okay. So we have Ranjit Gopalan. He works in data stage and now about to start a new project which involves Hadoop also. Great, Ranjit. Great. Hi, Prabhjot. Prabhjot is a founder of God Labs, and we work on machine learning and AI. Great, great, Prabhjot. And it would be great to know about you. And Prabhakara. Hi, Hi, Prabhakar. Okay. So, hi, Prabhakar. Prabhakar has got 5 years of experience in QA and 2 years of experience in Install Shield developer. Excellent, excellent. Well, so great, great. So Prasad is interested in Hadoop session and is new to this technology. Great. And we have Amjad. Amjad is 4+ years of experience into IT and SQL. Excellent. Okay. Anshul is a student as well as a junior Java developer. Excellent. Great. Hi, Arun Kumar. Hi, Rohit. Yeah. Yeah. So Rohit, yes, you're right. The webinar doesn't seem to work on Linux, and they seem to be working on something called a web viewer, but doesn't seem to work right now. So that is a big problem. And I would actually love to do all of it on Google Hangout, but Google Hangout also has got some problems. All right. So we have a great team over here, and let's jump in. So, first of all, before I introduce myself, let me tell you a little bit about No Big Data. No Big Data is a small company which we started 4 or 5 months ago. And the sole aim as of today is to convert training as a platform globally for all learning needs, specifically in the areas of big data. All right. So, that's our sole focus. We are trying to innovate in learning techniques in no big data by supporting various sample set, data sets, supporting building the environment where people can actually experiment and run things in real as well as virtual environments. So the biggest focus of no big data is to catalyze learning by promoting asking questions. Okay. and seems to be the difficult thing to do. And we provide something called learning management system, where we basically upload the whole videos, and there is a complete flow of complete storyboarding of which ones you should finish first and which ones should you finish later. All the quizzes, questions, everything is available in learning management system, and that learning management system will be available to you for lifelong. Okay. And the one thing which we have done differently from everybody in this industry is setting up something called cloud labs. Okay. Cloud labs is a concept which is like our own private cloud, to which we give access to all the students, and all the students can run their experiments, do the exercises, and do the research also on the cluster itself. Right. So that is something which we have done differently from all the other people, to avoid the thing like virtual machines. Although we provide you with the virtual machines, but it's not required. You can right away start working on all of this technology stack by connecting to our servers, and that's all. Okay, so that is something which we have done differently from almost all our competitors and everybody in this industry. So Cloud Lab is similar to what we were given at Amazon or in Mobi, where we had another team set up everything for us, and all we have to do is run our jobs and access the cluster. So in the similar paradigm, we have set up our own cloud labs. All right, and rest is just we try to provide you a socio-pro visibility. Lots of companies are working with us in terms of building their mm, building their manpower capabilities, so that as soon as we finish this course, in case you are open to it, we forward your profiles to these companies. Okay, and the companies include likes of IBMs and likes of your other service industry companies as well as product companies. So there are many companies who are working with us to be to to get great candidates. Okay. So Manikandan's question I would love to answer at this point. He has his question is, I have 8 GB RAM. What is the maximum size data I can handle using VMware and Hortonworks? So if you have 8 GB RAM and you are say having a Hortonworks sandbox running on VMware, so minimum amount of RAM you will have to keep for your native OS is 1 GB, and 7 GB you can dedicate to a Hortonworks sandbox, which should be 64-bit. All right. Now, out of the 7 GB, it lot of part will be devoted to various kinds of services such as NameNode. NameNode takes a considerable amount of chunk. Similarly, there are other services, specifically master. In all of these services, there are master and slaves. So masters generally tend to take more memory as compared to the slaves. And since in the virtual machine everything is on single node, most of your memory actually goes wasted in running all of these processes. So effectively, you will be left something close to after consumption of say 2 GB, you will be left with 5 GB of remaining. That too is very optimistic. So maximum you can have 5 GB for your processing. All right. Now, good. So because exactly that is one reason why we had started providing our servers, because virtual machine is not very constrained environment. You don't really feel that you are actually building something, because everything is on the same computer. You don't get the feeling that your processing is being distributed to multiple computers. Okay, so I'd like to move on because we are running short of time. Now this is me. This is a self praise about myself. So I finished my BTech in 2002 somehow, and afterwards I worked for 3 years in a company called DE Shaw, which only few people know about DSHA. It's a very small company in New York, and it's one of the biggest technology hubs from quite a past. Okay, it's one of the technology hubs. We had even Nobel Prize winners in the company. So there we built a very huge cluster long back before anybody else actually thought about distributed computing. And most of the architectures which we see as of today wasn't there, but we had our own similar kind of tools to churn huge data. Okay, I'm saying huge data because we did not call it big data that time. All right. So that time I mean, for example, Amazon's Jeff Bezos was there at D Shop. I mean, before I joined, he left. But lots of ideas about technologies actually have originated at D Shop. Afterwards, I started a company called T-Bits Global, and it was a large enterprise grade document management system, and it worked with very large corporates such as L&T Power, Tata Projects, and helping them build very huge power plants. All right. Then it was a product. Then I joined a company called InMobi and Amazon, and then at both these companies, I built big data solutions of very big scale. Okay, and then I founded in No Big Data this year itself, in 1st of April, and it sounded like April Fool joke, but it was true. So this is about me. Yes, Manikandan, that it was a finance company and it was in Hyderabad. Yes. Okay. So Akash is also from Roorkee. Nice. Great. And good. So all these are the 11 topics which we cover as part of 11 classes, and this is the first class which we are going to today talk about, and rest of the things are you know, the paid one, because you know, I too have some liabilities. So the first one is absolutely free. There are no strings attached. And in case you are not from development background and you, so the first one will serve you a great introduction. All right. So these are the topics which we are going to cover. So let's start. Let me, instead of answering this question, let me start asking you, like any other trainer, let me start quizzing you. So what is big data? What do you understand by big data? Whenever people say it's a big data problem, it's a big data solution, what does it mean when they refer to as data as big data? Good. So Anand says large amount of data in bunch, mostly unstructured, then volume, velocity, veracity, three V's, unorganized bunch of data. That's Manoj. Okay. Digital form of everyday activities. That's Kamalkar. Huge data, different structures of storage and faster access. That's Arun. And variety too. Good. Huge volumes of data without schema. That's Prabhakar. Something like a data warehouse or collection of data. Huge amount of data which having the high amount of velocity. Good, 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 great. So you all have a very good point. Now, this is the definition we will stick to. When we say big data, in very simple word, it's a data of very big size. Okay, big is an adjective and data is a noun. All right. So basically, So so basically it's simply a very huge data which you can't process with your usual tools like relational databases or existing file systems. And inevitably, you need a newer solution which can run on a distributed architecture. What does it mean by distributed architecture? Multiple computers. Okay. So let me rephrase what I'm trying to say. Data of very big size that cannot be processed by usual single computer solutions, for which you require multiple computers to solve your problem. And the data can be in any form, whether structured, unstructured, fast moving, slow, static, or it can be in any form. So in very very simple words, the moment your data becomes so huge that your single node computing, one computer, no matter no matter what you do. I'm sorry for the disturbance. All right, so let me turn it off. I've turned off my phone. Yeah. So the moment when your data starts increasing, and after a point of time, you realize that your relational databases or file system or any of the existing solutions has become a bottleneck, they can't handle it, as well as hardware of single computer is not able to handle that kind of data. Even if you keep on scaling this computer vertically, vertical scaling means we are increasing the capacity of single computer, right? So that doesn't suffice. Then we inevitably end up with a distributed computing. And the moment the computing becomes distributed, the whole paradigm of computing changes. The whole paradigm of computing just changes. Okay, starting with how do we distribute our computing till the point how do we coordinate with various computers, and that is the holy grail of whole big data solutions, and that is why people find it difficult to process, and that is why we require newer systems to be built upon, to be built such that we can run the same computing across the multiple machines. All right, so that is what is a big data. Okay. So this is what you need to remember. Whenever people talk about big data, almost every architecture has to be distributed. Okay. If somebody comes to me that, hey, I have got a great software which runs and can manage any amount of big data on a single computer. Okay. My simple answer is that you are fooling around with me. Okay. So, that is something you need to remember because, uh, I mean, the rate at which data is growing, the hardware is not growing at that rate. Now, this is the classic definition which IBM has been propagating. So, for the legacy reasons, I'll just go through this definition, but I don't really like this definition, honestly. So, as per big data, I mean, the definition of big data, IBM says that these are the four characteristics of any big data. First one is volume, second one is velocity, other is variety and veracity. Volume, as in you have got a huge data which is static. Every day it comes and it settles down in your data center. If that volume keeps on growing, then you will end up in devising newer solution. Then velocity. Even though your data at rest might be a simple integer, what if there are a million requests coming to update that integer? Okay, though your data accumulated is small. Okay, though the data accumulated is small, but there is a huge demand of from the users to update your data. Okay, data is not adding or gathering much, but updation is happening at a very faster rate. In those cases, we say the data has got velocity, and velocity itself is a singular characteristic would, after a point of time, require a distributed architecture. Okay, because each computer has got its own limits on number of sockets it can open. So effectively, you will have number of multiple computers running in parallel, catering to the demands of users. Okay, now that is called velocity. So velocity is one characteristic of data that might make it big data. All right, now third one is variety. So even though on first look, uh, 10 terabyte of movies is not a big deal. Okay, or 5 terabyte of movies or videos is not a big deal. But if you have to do a video analysis of this 10 terabyte data, it might become very, very difficult, right? Similarly, 10 GB of 10 GB of maps. Okay, 10 GB, 10 GB RAM is quite normal thing. So 10 GB of Google Maps would actually cover a huge amount of area. But when you try to find a path in this map, it might become really complex process. And that's what makes it a candidate for a big data solution. You might require multiple computers to find a path from one point to another. And therefore, the variety of the data might push you even if the volume and velocity is low. By the by by virtue of the variety itself, you might have to employ multiple computers to solve your problem. And that's what even a variety makes a makes a problem, a big data problem, quite often, right? Fourth one is veracity. Veracity is the case where you do not know where you will be throwing away this data or you will be keeping this data. So when you are in doubt, you keep the data, right? And that's what we call it veracity. Though we are not sure whether to keep this data or delete it, it might be logs, it might be a secondary computation of, say, average salaries of people in various age groups, because we might have the original data and that data would be the source of truth. But this intermittent data, we do not know whether to throw it away or keep it right now. All right, therefore therefore we, as a general habit, we tend to store it till the point we concretely say that we have a source of truth or source of data, better data available, right? So this tendency to store the data in doubt also makes it a candidate for also makes it a candidate for big data. Okay, so veracity itself will keep on making your data big and bigger, as well as it would lead to variety of. So is my voice audible? Suddenly it's giving me pop-ups. All right, all right. So where is the question box? I can't see the question box. Can somebody ask a question, because I'm not able to see the question box? So, okay, okay, I got the question box now. Good, good. All right. Awesome. Good, 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 good. Good. So the question box actually got hidden into the corner. So we were talking about veracity, and veracity might lead to high volumes as well as high variety of data, and therefore that might lead to big data, right? And now, trust me, every year IBM is going to add one more V to this definition. They started this whole thing with three V's, now it has reached to four V's. now I think somebody in my discussion was saying there are now five V's. The fifth V is value, and every time I'll have to justify their definition. Okay, so in very simple words, let's not, we. It's good that we talked about this definition because people might ask you that in the interview, all right, and they would be expecting you to answer in four V's. But the truth is, the moment your problem, your solution is not possible using a single computer, and you have to build a solution, custom solution, or build a solution on top of existing Hadoop kind of products. At that point of time, we say that this is big data. Okay. At that point of time, we say that this is big data. So that is the definition we should be sticking to. Okay. All right. All right. So, okay, just to test whether I'm talking to right audience, let me ask you a very, very simple question. How many bytes are there in petabytes? Okay. We, in every article, I see that there is petabyte. Everybody's talking to petabytes. And only few of those authors seems to know that how many zeros are there in a petabyte. And on top of it, we will discuss what does it really mean by that bigger data. How does it, what kind of computing it requires? Okay, will make you feel that what does it mean by a petabyte. Okay, so petabyte is basically, Rohit is saying 10 to the 15. All right, all right. So a petabyte is 1024 terabytes. Good. And a terabyte is awesome. Awesome. So I'm sure everybody knows it. So a petabyte is basically 1024 terabytes, and which is 1 terabyte is 1024 gigabytes, and so on till the till backwards. All right. So you can easily say that a petabyte is 1024 to the power 5. Okay. Kilo, mega, giga, tera, peta. Okay, kilo is 1024 to the power 1. Byte, mega is 1024 to the power 2. Giga is 1024 to the power 3, and so on. So 1024 to the power 5 in very simple words. All right. Any questions still here? And one byte is generally 8-bit, and 8-bit means it can store 256 states of anything. So that is the significance of a single bit. Now, very quick question based on our definition. Our definition said when the data grows big, it's difficult, and when it's difficult to handle using usual tools, and you require a cloud computing. You require multiple computers to solve your problem, a cluster computing. Then we call it big data, and one petabyte is 10 to the power 15 10 to the power 15 bytes. So, do you think these 10 to the power 15 bytes are big, I mean, can be handled easily by a single computer? So Rohit's point is, at the current rate of IO available in terms of storage and the limited capacity of RAM, it's not easy. That's very good point, Rohit. Thank you. So Amjad's point is that depends upon the processor. Now, before we talk about processor, even if we have a supercomputer, can we actually store 1 petabyte data easily on a single computer? Good, good. So in general, from our definition, I mean, everybody is coming up with their definition, so we'll stick with our definition. Petabyte is very, very difficult to be handled by any of the current file system. Whether you keep this petabyte in XYZ database or anywhere, they all are inevitably going to store in a disk on a file system that is going to be managed by some operating system. So none of the file system right now is so good that they can handle 1 petabyte data on a single node, right? So therefore, right, right. So therefore, 1 petabyte is generally characterized as big data, but that does not mean that 1 terabyte is not big data. Okay, that all depends on your usage of even 1 gigabyte of data, on how to handle. This is a general graph on how the data has grown. The digital storage has grown since 1986 till 2007. And suddenly in 2002, you see a sudden outbreak in the digital storage. And that's when we call the digital age started. And why did this happen in 2002? And why did we notice this happening in 2002? Because of these reasons. Okay. All right. So, so smartphones or the devices became cheaper and available and smaller. Cheaper, smaller, and faster. Cheaper, smaller, and faster. Because of the being cheaper and being useful, people bought it and therefore it became available. Now, because of the virtue of, just give me a second. All right. So, just give me a second. I am trying to optimize my bandwidth. All right. So, devices became cheaper, faster, and smaller, because of which there was a revolution in amount of devices which were available after post 2002, and therefore the digital era started. Also the internet got easier to set up. The more and more connectivity started happening, connectivity became easier and possible. And afterwards, the the social networks started, and social networks made it possible for people to communicate more and more and easily. Okay, basically softwares came into play which connected people by the way of videos, by the way of simple text, by the way of photos, everything. Okay, so since hardware was there, and therefore the softwares evolved, and that made digital era what it is right now. Okay, so the connectivity improved, device became cheaper, faster, and smaller. These are the three characteristic of any. These are the three targets of any device manufacturer. Always, okay, they have to build device cheaper, faster, and smaller. That's their key objectives. All right. So now this is something different we are going to talk about. This is little technical, and trust me, unless you understand these aspects, you would not really feel the need of why do we have a need of distributed computing, right? So let's start with something, the heart of the whole processing, the brain of of a whole computer, which is CPU. CPU is basically something which reads instructions and act upon it. Okay, CPU is one which understand instructions and act upon those. So CPU is the main you know the main unit which is used when we do anything in the computer. All right, whether we are uh, you know sorting the data, we are running a software, or we are trying to store something by the way of hardware, then also the CPU comes into picture. mostly. All right. Now, second is RAM. RAM, in case of RAM or any memory, both aspects, how big is the RAM and how faster it is. Both the things play a humongous role. If you keep on increasing RAM alone and your processor is the fastest, after a point of time, the bus which goes from CPU to RAM becomes the bottleneck, right? And that's where after a point of time the CPUs have stopped growing, uh, unlike the unlike the earlier time, right? So the bus or the rate at which we can read from RAM is also one very important criteria. Now, third one is the disk size. Disk is storage where we store the data permanently. Permanently, as in even if the electricity goes off, the data stays there. And the size as well as speed both matter a lot in computing. All right. Now, fourth one is network. Network is something which was never counted as a pillar of computing before say 2002, 2004. Before that, network was never considered. But now, if you have got huge data and you cannot store it on disk, you will be storing it on the network. And when your processor needs to process the data, it will load the data from the network to RAM and then start processing it. Now, if your network is slower, or if you're doing a lot of network reads, then your network is the bottleneck. So these all four pillars, when you try to solve a big data problem, one of them will become the bottleneck, and you will try to take out that bottleneck and try to move it to another bottleneck. Say your disk became a problem, so you put it in a network. Now network on a network drive, right? And when you access it again and again, the network chokes and network bandwidth becomes your bottleneck. Now similarly, if your say the speed of your disk, the rate at which you read from disk is quite slower. It's like around you know at a magnitude of more than 10,000 times slower as compared to RAM. And therefore, you try to cache it into RAM. After a point of time, RAM becomes an issue, and you keep on increasing one or the other of these components, and you will still get stuck with a bottleneck somewhere. And that's where the big data problem starts. That no matter what you try to scale up in these hardware terms, you are not really solving your problem. You're just moving a problem from one to another of these pillars. You are roaming around with these things. Okay. So if you start increasing RAM and you are able to load hundreds of GB of data into the RAM, your CPU will die of computing. Okay. So therefore you keep on moving as part of your programmer or as part of developer or as part of administrator. You keep on moving the stuff, moving the bottleneck from one to another. And at a point of time you give up and then say, okay, we need to devise some other solution. And that's where the realization comes into picture that we need multiple computers to solve it. Now, since these are the four resources, and when you have one more computer identical to your first one, you are actually making your resources, total number of resources, 16 times. Okay. So each of this is getting doubled, remember? And if you, I mean, your computing generally is a result of multiplier effect of all these four. So therefore it is very important to understand that these are the four pillars on which you keep on roaming around. Okay. In computing, you start caching stuff, which means you are putting stuff from to memory from the disk, and then after a point of time you start moving some data from RAM to L2 cache, L1 cache to make the RAM speed faster, meaning the IO speed faster. All right. And basically you are roaming around in this. And that's the role of a engineer, software engineer. So at least one of these will become bottleneck when you deal with big data. Okay. Now the general pitch of big data. So I have been using recommendation engine. I have gone through ad targeting. I have tried to improve search quality and have done a basic sentiment analysis, but have not done abuse and click fraud detection. But I have done a large scale, large scale money laundering detection, anti money laundering, right? So these are so what is the recommendation engine? Based on the behavior of user in past and the behavior of similar users in past, we give the cross sort of a recommendation, which is cross selling, right? Sandeep Giri and say Kumar, Sandeep Giri and Kumar Swamy has got similar taste in movies. We figured out based on our history, and we start giving recommendation from one to another. That is the most simple definition I can give you about a recommendation engine. Recommendation engine is is a very popular usage of big data solution. Okay, and this is not something hypothetical. This is used day in and day out. At Amazon, the recommendation of products generates a lot of lead and conversions as compared to any other ways of marketing, right? Similarly, ad targeting is not something hypothetical problem. Everybody is already using it. Okay, starting with Google, InMobi, and other ad players, Yahoo, and everybody, they're all using a huge data or huge big data solutions to solve their problems. So ad targeting is something a common problem to people who are serving the ads, specifically advertising companies, ad serving companies such as Google AdWords, for example. So there are millions of people who are using the mobile phone at the same time, and they're all playing with one app or another or opened a browser. Everywhere everywhere people show ads, okay, at the bottom or the corner, and those irritating ads are everywhere. Now at the same time, if you look at from the perspective of Google, that there are every se- every second there are hundreds of thousands of requests across the world for ads. All of these requests are asking Google to give me ad so that I can display on this real estate. And now imagine the complexity of problem that in 1 second you have to take a judgment call based on demand and supply, that which ad to serve and whose bidding is higher and all of that. And that cannot be done unless and until you have thousands of computers in an array serving to the end users. All right. So that is ad targeting. Search quality is one such thing we you all need to understand. I'm actually building another course to just focusing on how to solve your searching problems. Okay. So search quality is an important issue. Even if you are a very small company, you have built a document management system for a user base of say 20,000 users. All right. 20,000 is not a big number, right? My product was serving around 10,000 users, more than 10,000 users actually, over a period of a week. Total number of accounts we had were above 20,000 users. Now, think about this. When user searches, even though your data is smaller when I say it might be say 200 GB, and you want user to get the perfect results. So say user want to search for blue space dart or blue dart, right? Now you have to do a lot of magic, such as when people type in blue, you have to figure out the suggestion that it would be dart. Okay, so this could be done based on after churning this 200 GB of data and figure out the tuples, we call them tuples, who come together generally, or all n tuples again. Two tuples means two words which come back and forth, means together, and three words which come together. So based on this data, you will have to build auto suggester, which gives them a quick auto suggest. So when you are building search quality, there are hundreds of such problem you need to solve. So you have to build aliases in case people are searching for say garden. You should also be giving results for gardening, right? So there are hundreds of parameters which you need to consider while building a simple search, right? And those parameters, they can be better built if you churn a huge amount of data and use that data as a dictionary for various kinds of things, as a thesaurus, as a autocomplete, as a you know figuring out which word means what. Okay, so that is the holy grail of search quality. Now now there is something called sentiment analysis. Sentiment analysis basically says that what is sentiment of the public as of today about my brand? And tomorrow, if I launch another campaign or another advertisement, I put more hoardings on the road with a new advertisement. What is the sentiment analysis of the world towards my brand? Is it improved or has it gone down? We launched an ad yesterday, and then has my traction gone up, gone down? And is it computed? How do we compute such kind of thing is based on we compute this kind of this number based on positive words and negative words used in the same sentence against your brand. All right, and it's a when you deal with big data, so most of the time you will see that a simple average of value will solve your problem. So even if you just figure out all the keywords, negative as well as positive, used with your brand name, and you just sum all the negative values and a positive value, and there is a score if you combine those two, and that will give you your sentiment, the general sentiment of your brand. Is it positive? Is it negative? Is it going up? Is it going down? Just even if you do a very simple thing as summing up, just tagging all the words as positive or negative, give them a number value, and that's all, right? This dictionary you can build it or you can download from various sources. This kind of dictionary where each word is negative or positive and how negative is it is given to you. All right, so adjective, whether it's noun, all of it is available. Now this is called sentiment analysis. This is probably the very simple problem to solve as compared to the recommendation engine for the demonstration. But the problems beneath these, all of these four, are every day people are improving, and people are making it available as part of libraries here and there. And then last one is abuse and click fraud detection, whether people keep on clicking on the ads to gain the money, which is not good idea, has to be detected. Similarly, there are a lot of things can be done at telecommunication. People are actually doing all of it. They're figuring out why do customer leave us, why do customers leave our telephone service. So all of this is actually happening. This was unimaginable few years ago. And now it is all possible just because our ability to store the data and churn the data has dramatically improved. And this dramatic improvement has happened by virtue of being able to utilize 10,000 computers or 100,000 computers together simultaneously to solve your problem. And that's what has changed the game in the enterprises as of today. All right. So these are the other examples. Then there are hundreds of examples. All I have done here is I have picked up the use cases and the case studies from Hadoop's website, Hot and Works in Cloudera. And these are the few examples I have picked up. Now, these are the other companies which use Hadoop. This is specifically for Hadoop in a real sense. Okay. In this, somewhere we have, um, do you see InMobi? Yeah, here is InMobi. That's where I was working. And do you see Amazon? We have actually at Amazon. It's just that these guys don't know that we have at Amazon. All right. So the size of the word in this one means that how big is their cluster. So Yahoo has got the biggest cluster, and InMobi also has got a decent cluster. All right. So any questions, guys? Any questions? Feel free to ask the questions right now. We have got 33 people in the batch, and that's great. Now, this is like optimum size of the batch. So feel free to ask a question because I see that you guys are not asking questions. Okay, Arun's point is what is a cluster? Cluster is when you take few computers, connect them together in a network. It's called a cluster. Okay. So what's the use of big data? I said as here, if you see this one. So when you build a recommendation engine, as I was explaining, the bigger the data, the better answers you will get, right? The bigger data you have more people similar to each other, and you will have more recommendation to be given from one person to another. Recommendation, how does it work? I'll just explain to you in a very, very overly simplified manner. So, say for example, myself and Deepu, we have 5 movies in common. Out of 6 movies we have watched, both of us, 5 movies are common, right? And which means that we have a very similar choice. And therefore, we can say, ask Deepu, hey, what was the 6th movie you liked? Maybe I'll watch that one. And similarly, I can tell Deepu that, hey, this is the 6th movie you should watch. Rest movies you have watched. So we gave one recommendation to Deepu and Sandeep Giri, and that's what a recommendation engine is. Now imagine that you have more and more and more and more users, so that you can find a very very m- more and more cluster, right? If you have 3 people now, 3 people, if all 3 of them liked 5 movies out of 6 movies they have watched, now your confidence level is very high that all these 3 people whose 5 out of 6 movies are common, they are very very similar in nature. And if you have 4 people having such a similarity index, such a similarity between their behavior, that means those 4 people are like very close to each other. And as and when the numbers keeps on growing, you have more chances of having a great cluster. Okay, and hence you there are high chances that you will be able to give out really really good recommendation to each other. Okay, so that is now, so you can get a great recommendation if you have a bigger data. Okay, and if you have a bigger data, you have got a bigger data problem because you need to churn these recommendations using multitude of computers. Okay, so therefore this is one simple use case of big data, and the other use cases are similar in nature. Sometimes you want big data and sometimes it's inevitable, right? When you are building recommendation, it is inevitable. You want big data. The bigger the data, happier you are. But in the cases like ad targeting, it is inevitable. The more customers you have, the more ads targeting they will be having, the more ads they will be requesting, and hence you would require systems which can serve ads parallelly to so many users with a good relevance. There is a term called relevance. All right, all right. So Deepu actually did not hear. So Manikandan is asking for a picture on Hadoop. Don't worry, it's coming up in the right. Big data is basically managing data or manipulating data. So big data is data. Okay. Big data is not a verb. It's not an action. Big data is big is an adjective to the data. So big data is just big data. And big data problem is managing and manipulating data. All right. So your point is right. Now, Can you give an example of a recommendation engine? Ranjit, was I able to successfully answer your question just now? So Mahesh's question is, if Yahoo has got a largest cluster, how about Yahoo? So how about Google? So point is here, I was talking about Hadoop clusters all across. Okay, these are Hadoop clusters. How does big data play? That is Anand's question. How does big data plays in banking sector? The answer is that yes, there is a huge place, but most of the records which are relational in nature, where we want relational or transactional data, is not really well solved by any of the solutions available, any of the tools available. Okay, but there is a huge requirement in every sector. I see Goldman Sachs, Morgan Stanley, everybody asking for big data solutions every day. Hadoop is the tool to manage big data. Yes, that was Arun's question. What about big data penetration in India? It's huge. I know hundreds of companies who are using big data in India and to really fruitful level. Is it a long way to go? No. It's already there. People are using it. It's just other people who are not aware, they're catching up. All right. So I hope I answered your questions. So should I move on? So these are the general common myths. You can go through these myths, and if you are still convinced about a myth, you can ask me right away. I can answer your why is it myth? I can answer. So always big data always means data above our range of terabyte. As I explained that even 10 GB of map manipulation or graph manipulation is a very difficult thing, right? And it might require a bigger data solution. So therefore, 1 TB or bigger does not always mean big data. The moment you say that my single computer doesn't handle or solve my problem, it's a big data. All right. So these things you can go around this is a general graph where I've compared the kind of job requirements and salary ranges which is there. You can also look at indeed.com and naukri.com. This is just to tell you that there is a demand and supply gap. There is a demand from many people, and supply is not there in the industry, right? There are lots of people who need to know learn this technology properly, not only learn the keywords. Okay, so there's a huge disconnect, and therefore the salary difference is there, right? All right, so let me just check what's time. So was I able to answer your questions? Great, great. All right, so it's 9:15. We have All right, so we have covered 1 hour. Great. So now let's start with something called Hadoop before we jump into anything. So we will start with the basic definition. So we made it clear that we needed a distributed computing. So is Java experience must for big data? That's Balakrishnan's question. Answer is no. Lot of my ex-students have been from non-Java background and they have been done fairly well in solving most of the MapReduce problems, right? So basically, generally, the Java is required for MapReduce computing, but we have been able to successfully convert all the MapReduce problems into language agnostic way, right? By using a technique called streaming job. So therefore, you don't require a Java experience to learn MapReduce or Hadoop. Okay, it's a general concept. Now let's talk about Hadoop. So Hadoop was created by a guy called Dog Cutting, and Mike Caffarella joined him later. And Dog Cutting was working on a, a search engine project called Nutch, and he named Hadoop after the toy elephant of his kid. And Hadoop, he has made it open source Apache, and that's what has been the groundbreaking thing. Because any software which has been Apache license has been widely accepted because it's okay to use the software in commercial applications, right? Without having to pay anybody, as well as there is no obligation of any sort from Apache. Therefore, almost all the Apache softwares have been fairly successful. All the software which has got Apache license. Therefore, so that is a very big point with respect to Hadoop. Unlike SAP, HANA, or any of those solutions which are proprietary or other softwares available in industry, Hadoop has got biggest support because of their licensing. Now it's quite powerful and popular and supported. And this is basically a framework, one of the many frameworks to handle big data. Okay. And all the components under the umbrella of Hadoop are built with an objective of reliable, scalable, and distributed computing. Okay. All of the components from bottom up. So basically, Hadoop started with simple file system and a compute engine which were inspired by Google's paper. Google has published three papers concurrently, one on file system, other on compute engine, and third one was on database. And most of the Hadoop is actually based on those papers. All right. And since it is to become popular, and there are almost every kind of machine which might be utilized in future to run Hadoop in a cluster, it was written in Java. Okay, because Java runs almost on all machines. What is the scope to switch from advanced Java to Hadoop for experience? There is a huge scope of switching from. It's not switching really, it's just basically learning a new technology, and knowing Java is an additional feather. Okay, for you, life will be little more easier for you. Okay, but technology per se is quite important, and there's a huge stack which need to be learned. So there's a lot of scope. Is mathematics, calculus integration plays an important role in big data? If yes, how and where? That is Anand Gadkari's question. So all of the basically calculus and integration is rarely used as compared to statistics when you are churning big data. All right. Only in case of few situations such as you are trying to figure out a pattern in the input data, periodicity in the input data, only in those cases you might do a Fourier analysis and do a fast Fourier transformation. Only in those cases you would require to do a fast Fourier, which is internally an integration. You would require that kind of computing. All right. And rest is basically up to the data sciences people who are deep down in data sciences, and it all depends on problem to problem, how what you are trying to actually solve. But more important than a differential calculus is your statistics. Okay. Your ability to basically group various people given on various characteristics is a very more important, and even a simple average computation is important, right? So calculus, as I said, was is a rare attribute, but that's generally required when you are going for advanced algorithm building. Now, this is the component. Somebody asking me about the component architecture. So we'll go by one. So first of all, let's talk about. So this is the whole Hadoop ecosystem. It has everything in it. So we'll talk about first the basis of the whole game called Hadoop file system. Okay. Now, a Hadoop file system is the main component of a newer file system which runs on multitude of computers. Okay. Now, before I jump into the detailed description of what is HDFS, I want you to work with me on one particular problem. And the problem goes like this. The problem statement is, say you have got 100 terabyte of data. You have got 100 terabytes of data. How would you store this data? And trust me, there is no hard disk in the industry which has 100 TB size. Okay, it might be in the labs of CDAC or in IBM, but in real commercial uh, applications, not there. Okay, so let's assume that you have got maximum size of hard disk as 1 terabyte. Okay, now 100 terabyte of data is not unusual. If you are 100 people living, or say 500 people living in a locality, if you all decide that, hey, let's just build a local movie storage so that we all can just access these servers and start watching movies. All right, that is the objective. How would you build such a storage? I will have a patience and you answer the questions. Okay, we'll work together to reach to a conclusion that HDFS is really a brilliant solution. So Manideep's point is that on a server with quite good config, but you see the 100 terabyte is not possible to, connect to one server, right? And as I said, like there are 500 people, right, in this locality. So now my point to you is that how do you build such a storage? We all talked about petabyte of data. Right now we are just talking about 100 terabyte data. All right. On cloud, Amazon, AWS, and S3. That is Mahesh's answer. And yes, that's a clever way of not building things. But here, I'm looking forward to you as an engineer who were asked by Amazon long back to build AWS. Okay. So Mr. Kumar is saying that have master and slaves. Yes, that's a very good point. So go ahead. Go ahead. Yeah, give me any solution which you feel is good. Okay, it doesn't have to be perfect. It doesn't have to be, you know, groundbreaking. Just whatever you feel like. If you are in that situation in day-to-day life, and you all of 500 people in your apartment decided that, hey, let's build a local movie storage. What is it that you're going to do? Okay. So Ranjit's point is there are two ways. First is distributed. First is distributed. Okay. Use a file system with a hash map kind of structure to connect the data. Very good point. Go ahead. Go ahead. I am looking for more details. Now Mahesh's answer is sharing movies folder to the network. Okay. 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 Possibly cluster FS or SAF for distributed object storage and retrieval. Okay. Okay. So I'm assuming that these file systems are there for distributed storage. Go ahead. Cool. So anybody answering? Compressed storage, but uh, movies itself is a fairly compressed object. You cannot compress them further. Okay. Microsoft Azure. Okay. So Microsoft Azure is what on the back end it's mostly HDFS. Right. HD Insights is basically a Hadoop, and Azure also uses a similar mechanism. Cool, cool, cool. So somebody said sharing movie folders, and yeah. So back in 2000s, this is what people used to do. What they will do is they will connect these hard drives to multiple computers and connect those computers to a network. And then using network file system, they will mount these files everywhere across the whole cluster. So on every computer, you will see drive 1, drive 2, drive 3 as a subfolder of one main folder. Okay. And these are basically remotely mounted folders on all the nodes which are in there. So this was the general structure we used to follow earlier, okay, using our network file system. We have a main folder under which we created multiple folders which are basically mount remote mount of the hard drive. Okay, this was the general solution, and on top of it what we used to do is below every drive we used to put one more drive as RAID 2. Okay, so in case the hard drive fails there is a backup on that particular machine, same machine. So this was the structure we always followed. And do you see any problems with it? So did you understand this? So what we did was we connected these hard drives to multiple computers in the network, and using a network file system such as NFS, we mounted remotely these file systems onto a local folder. So to a end user who is connecting to the one particular computer, all of these hard disk will look like subfolders of this folder. All right, he doesn't have to do much. Okay. So now Rohit's question point is that there is one problem he has pointed out, that what happens when one node goes down, right? This is a very valid point. So there is no failover, because even though we have RAID, we said we have put a replication of this drive 1 onto the same machine, and therefore there is a replication on that node, right? But what happens in case one computer gets shut down, or network cable is bitten by the by the mice? Okay, and it's very common in data centers. So in that case your data is lost, whatever was there on that particular computer. Also, there is no way to index data for fast retrieval. Yes, so there is no right away solution. So what people generally do is they build a crawler which goes through all these folders and creates indexes somewhere, and then everybody looks at that index. But that's, you need to build it. It's not there right away. Yes, so Deepu's point is that it is difficult to maintain the data. Very good point, right? Similar to Rohit's point that there's no easy way to index. It's also a valid point. So it's difficult to maintain the data, as in when we try, you got a new file of few GB and we tried to fit in the first drive one, and the drive one did not have enough space. We went to the drive two and we kept on moving until we found the enough space to store this file, right? And we need to keep track of which file we kept where. Right. We don't know how many copies to make also. Okay. Okay. Any other question problems do you see with this kind of structure? All right. So let me So we pointed out a problem called failover and backups. In case one node goes down, the data on that node is lost completely for you. It might be safe on that computer because there are two hard disks, but it's not unusual that one computer burns down. It's quite usual thing. And in that duration, somebody has to manually diagnose that hard disk and figure out how to retrieve the data from the backup, right? There is no failover. And if you see, for the end user, the data is not really backed up. It's lost with that computer. It's very common to have fires in the data centers, right? Second one, the indexing problem somebody pointed out, I put it as like, how would you distribute data uniformly, right? Whatever scheme you make, that okay, all the movies starting with A, we'll put it in these computers. Movies starting with B, we going to put in these computers. No matter what kind of scheme you make, it is going to be really inefficient, okay? Unless you really build a randomized solution. Okay, so this distributing data uniformly is also referred to as sharding, 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 in lots of scenarios. Okay, even when we talk about big data, we always call it the sharding problem. All right, now the other question that arises is this the best value for many? Are we putting best use to resources? Because here what we did was we took 1 terabyte drives, we bought new ones. Even though we might be having smaller drives, 50 GB, 60 GB, 80 GB, 100 GB, 200 GB in the our already available to various people, right? Now, other thing is in this scenario, the smallest drive we can use is should be bigger than the movie size, right? Otherwise, we won't be able to fit a movie onto that hard drive. Now, the last problem which most of us forget to address is right. So the last point is what about increased availability? The moment a new movie comes in on that Friday, all of your 500 people would want to watch that movie, okay? Same day or maybe within a same window of an hour. All right. And that point of time, the computer which is hosting that movie will get choked by so many requests and get shut down, and everybody goes panicky. And this is called accessibility, right? You can imagine the same thing with YouTube because YouTube is storing so much of data. And a new movie has got a bigger demand, and the movies which are trending higher will have bigger demand, and therefore YouTube had to figure out how to handle these kind of high demand things. All right, to solve exactly this kind of problem, people designed HDFS, or Google designed Google file system, on which everything is based on. All right. Okay. Okay. All right. So Harpreet's question is, he has 4 years of experience in manual QA in product-based company. How good it is for me to switch to Hadoop? It's very good because uh, there are there are newer set of technology, newer set of challenges, and whether you are in QA, DBA, or mainframes, SAP, ERP, or any of these domains, all of these domains are going to get impacted by the newer set of technologies. So, uh, I mean, it will be great if you learn these technologies. All right. So this was what we talked about HDFS. Today we are doing really good with respect to time. All right. So do you have any questions for me on to this? Yes, Spark supports HDFS. All right, now let's move on. So let's take a break of 10 minutes and we'll come back at 9:40. So Manideep's question point is that what are the differences between Hadoop and Spark? That I'll not be covering in this session, but if you drop me an email, I'll make sure that I reply to you. All right? Yes, Kumar Swami, everybody is muted by organizer, and therefore the only way to ask a question is by typing. All right? So have your dinner and come back in 10 minutes or 12 minutes, let's say. Okay, so should we start now? It's already 9:40. Okay, so Deepu is back. Okay, great. So should we start? Perfect, perfect. All right, so here we go. So before the break, we were talking about something called HDFS. All right, and why did we need it? We discussed a particular problem statement where we were trying to store 100 terabyte of data. And to store that kind of data, the normal solutions do not work really well. Now, we are going to go into details of what is HDFS and and how does it work. Okay, so HDFS is basically a very high fault tolerant system, and which can store lot of data using thousands of computers. Okay, without any problems. So here we go. So in an HDFS cluster, or when we say cluster, cluster means a group of computers. All right. So in an HDFS cluster or Hadoop file system, there are two kinds of computers. One is called name node, and there are other kind of computers which are called data nodes. Okay, it's a straightforward, a master slave kind of architecture, whereas name node or admin node does only stores metadata, while actual files which you are trying to store, the movies, the all kinds of data, is actually stored in data node. All right, so the actual data is stored in the data node. So here, as you can see, that actual files are on data nodes while the metadata is on name node. So whenever we store a file in name node it asks us to split it into small chunks and stores smaller chunks, these small chunks, into various data nodes. Okay, so each file is split into chunk of size 128 MB. Nowadays it's 128 MB chunk size, and stored in on multiple data node, which means that there is no single bottleneck of the system. All right, and here basically admin node does not do anything per se. We go to admin node, we tell admin node that we are trying to store this movie. Admin node responds back saying, why don't you go to these nodes and store first and split your movie into these five portions and store this portion on this machine. That's the reply admin node gives us back. Okay, and we go on to each data node and do it. When I say we represents the interface, that software command line you are going to use, or the driver you're going to use to interact with HDFS cluster. So that the driver, the software, the command line, the driver does all of this for you. It goes to admin node, tells, hey, I want to store this file. Admin node tells you back that you go to these nodes which are connected in my cluster and store your first chunk here, second chunk here, third chunk here. Okay, I'll be using the word chunk interchangeably with the block. Okay, so a file, when you go to admin node, it asks you to split it into blocks and then divide it onto multiple data nodes. Okay, now this is big file is split into small portions and saved onto the network. The other important thing which it does is it says that the replication factor. The default replication factor is 3, which means each block is replicated onto 3 computers. There are 3 copies. There are 3 copies of each block lying in the network, which means that even if one data node fails, it doesn't matter, because anything that gets lost with that data node is another computer running a process. It can fail, right? And in case that data node fails, the data is secure, which is there. The other 2 copies of each block which is stored in this data node is available in the network, right? And therefore this architecture actually solves it, right? Now, on the name node, metadata node, the only information which is stored is what is the file name which we have stored, what was the actual size of that one, and what is the data nodes on which this file is stored, how many blocks, which block is on which data node. That kind of mapping is taken care of by name node. All right, so is the architecture clear to everybody? So there is a name node and there are data nodes, and every file is split into blocks, and these blocks are replicated and stored in the network. Okay, now the moment one data node goes down, because the moment a data node goes down, we are only left with two copies instead of 3 copies of the blocks which got lost because of this data node loss, right? Now, in as soon as one data node goes down, name node informs various nodes to start copying the blocks which have been lost, so that the replication factor is balanced back to 3 instead of 2, because when replication factor means how many copies of a block are there. If we say replication factor equals 3, which means each block or each chunk or each piece or each portion of the file which is stored has 3 copies. Okay, so if all these 3 computers on which a particular block is stored, if all of these 3 go down suddenly, simultaneously, then your data is completely lost. Okay, and but the probability of that happening is quite low, right? And since there is automatic balancing, the moment a data node get lost, the data that gets lost due to that particular node, you the those blocks gets copied to other machines, which means in a few minutes you will have those blocks again as 3 copies rather than 2 copies. All right, so I'll answer Deepu's question. So what kind of data is stored in admin node? Admin node basically stores the information like file name, what are the blocks, where are those blocks, and this information. All right, so was I able to answer, Deepu? What if the file size is less than 128 MB? In those case, the block size will be smaller. Okay. And also that will be the case where even if your file size is bigger, the last chunk will always be smaller than 128 MB. Very good point. Okay. Now, how does this is best value for money? What about increasing accessibility? Okay. Okay. Thank you, Anand. Now, these data nodes, These data nodes can be very small, or hard disk can be very big or small. It doesn't matter, right? Say you have got a Blu-ray movie which takes 200 GB space in the disk. 200 GB we are talking here. Okay. Now, when the smallest disk you require, beyond which you cannot go smaller, is 128 MB, right? And therefore, whatever disk is available in the market at the cheapest money, you can buy them and dump into this network, and it will still work perfectly fine. And and this was the architecture Google followed when those guys were in the college. They bought the old hardware which people were having, and they started using those hardware. Was he able to answer, Anand? Now, Kumar's question is really interesting. He says that, is name node a single point of failure? Generally, yes. But there are two more concepts. One is called backup node of admin, backup admin node we call it, which is basically whatever metadata is there in admin node is continuously backed up to admin node, or to the backup admin node. Okay. Similarly, there is a secondary name node. Secondary name node contains the transaction log as well as the you know a little stale state of the data. Okay. And you have to manually bring it up. So secondary name node is not really immediate failover, but the backup name node, which recently has been done, actually stays in a cold state, and the main name node remains in a hot state. The moment name node goes down, the the backup name node will take a place. All right. All right. So I hope I was able to answer your questions. Feel free to ask your questions. And the whole objective of these sessions is to be able to answer your questions. There are hundreds of resources about this information across the world, but uh, to get your answers when, as and when you get a confusion or a doubt, is the sole objective of these sessions. So feel free to ask any question as we discuss. Okay. All right. So is this architecture clear to you, or should I walk you once more through the game that happens? All right. So okay. Is there any particular limit on how many data nodes a name node can serve? Mm, so basically, there is no particular limit per se. The only limit in this whole game is how big a RAM you have in name node. The data which is there in the name node is a disk supported RAM, which means all of the metadata is always loaded in the RAM and is saved onto the disk continuously, which means that in case the RAM is smaller, you will have name node will be forced to retain only small data, which means that it will start increasing the block size from 128 MB, which is default, to a bigger one. Also, that will also dictate that number of data nodes it has to deal with. If they grow beyond a limit, it won't be able to handle it. All right. So the RAM of the name node will be the bottleneck when you increase the number of node. Okay. Okay. So Arun's point is that once more, but could you just repeat the question? Which one you are asking for? I don't know which question you are asking me again. So could you repeat? Okay. So Anand's point is, based on what admin node suggests to the interface to store into the data, how does it decides? Based on what admin node suggests to interface to store into data store. Very good point, Anand. Anand's point is that what are the parameters based on what the name node will tell you that these are the data nodes where you have to go and store. Why does it say data node 1, 2, 3 instead of saying 2, 3, 4? Right? So name node maintains a virtual state of all the data nodes. It maintains how much disk available on each one, how much memory is available in each one, how much, what all files it sent earlier. Because whenever you are going to insert anything into HDFS, you always go to the manager, which is name node, and tell him, hey, I want to store this big file. Okay, and this name node makes a note in its memory and says that, okay, so what I'm going to suggest to you is, why don't you go to these data nodes and store this, divide your files into these 10 blocks, store first 3 blocks onto this node, and these 3 blocks into this node, and 2 blocks onto these nodes. Now now in case, now all of this information is available with the name node. And it also tells you that once you are done with writing into data node, please come back and confirm. Okay. So once if the user does not confirm, if the driver does not confirm, or the interface, command line interface does not confirm back to SDFS ki, hey, I'm done, it does not store anywhere. Okay, it will just discard all the notes it made. That is how this name node behaves. All right, that is how the name node behaves. So those are the reasons, and based on this structure, it it keeps a track of what is where, and based on what is where, it gives a recommendation. All right. Now, good. The previous slide. Okay. Okay. So I'm again going to describe the same thing which I was describing earlier. You have got name nodes and you have got data nodes. Here you can see there are these 5 data nodes. All right, name node and data node. The client who is going to write the data goes first to the name node and tells, hey, I want to store this file. Name node in return tells the client that, hey, go to these data nodes, put the blocks on these machines, and then we will talk further. Once you are done, just report back to me. Now client will start directly storing the data onto these data nodes. Now why doesn't name node accept the read write request from the client directly? He could have made the life of the client easy, right, by you know taking all of the file from the client and start splitting it and dividing it amongst data nodes, right? He could have done that, but he doesn't do it. Why? Anybody quick? Anybody quick? If it starts reading writing data, then name node will be the bottleneck in the whole game. Right now, name node saves itself from the real node. People come to it, it immediately answers them and disconnect. Okay, that way name node makes itself as free as it can be, so that it is not impacted by any of the load problems. Okay, right? So Arun, is it clear now? So this is the previous slide. All right, and good. Now we are moving forward. I was trying to answer Arun's question, and then we have Okay. Does Hadoop act as a data store or a tools which does MapReduce processing? That is Ranjit's question. So Hadoop is a suite of components, and we are talking about the first one called HDFS. There is something called MapReduce, another component which lives on top of this file system. Okay, and this is what we are discussing right now called HDFS is the base of the whole thing. Great, great questions. And serving of a file, that is Kumar Swami's question, I'm repeating. Serving of a file by fetching the data from all data node. Okay. Does it happen through the name node? So can we call it as a bottleneck? Yeah. So I was explaining exactly the same point. In case name node starts serving and reading and writing through itself, then name node will become the bottleneck, and that's what he does on the first instant. The moment you talk to name node, hey, I want to write this file, it replies back saying ki, you don't give me the file, you'd go directly and write on the data node. Okay, so that's what it is. All right, was I able to answer Kumar Swami's question? Okay, okay. Kumar Swami actually was, I think, answering my question. Not sure where this place available. Place, place. Yep. Great. Now let me just move ahead. Now let me just move ahead. So this was what we call HDFS architecture, right? Now the name node is master of the system, maintains, manages the blocks which are present on the data node, right? And then data nodes are the slaves which are deployed on each machine and provide the actual storage, right? Data nodes are responsible for serving the read and write as I described. And this is the whole anatomy again, whatever I described earlier in the fashion. Somebody was asking me what kind of metadata the name node stores. This is the kind of metadata name. So it's a file name, number of replica, block IDs, what are the blocks, and so on. Okay. File size. So except for the transaction log, everything remains in memory. Also, there is a copy of the memory is maintained on the disk in case there is a power failure. It doesn't lose anything, right? Transaction log is not maintained in the memory. It is maintained in the file system. In general, what is metadata means? Okay, metadata is data over data. Right now, our data was a file which we were trying to store. Now, when we splitted it, we made say 10 portions of it, each of 128 MB. Now, this information that how big the file is, how big this data is, how many chunks are there, what is the size of the last chunk, that is a metadata. Okay, so metadata is basically data of a data. All right, so metadata is basically data on top of data. Great. Should I move on? Now the next one is the compute engine. Okay, we call it yarn. On top of yarn lives paradigm like MapReduce and Spark and other things. Okay, so yarn is basically yet another resource negotiator. Before we get into the compute engine, I want to ask you a very simple problem. I just want to understand the your gut feel. Okay, say you have 1 gigahertz processor and you are sorting 1 terabyte of data. And what kind of 1 terabyte data it is? 10 billion names having 100 characters each. That is 10 billion names, right? Now, how would you order it? Sorting means ordering it in descending or ascending order, whatever is your choice. Okay. The RAM available to you is 2 GB. RAM available to you is 2 GB. So how long does it would it take for sorting this 1 terabyte data? Any gut feel will do. Any gut feel. 1 minute, 1 hour, 1 day, 100 days, anything. So you got only 1 terabyte data, and 1 terabyte is 12 zeros. Okay. Kumar Swami's point is that probably a lifetime. Okay. Anybody else thinks that it's a lifetime? All right. Anybody? Just any rough figure will do. It doesn't have to be very precise. Even 5 times wrong is okay. All right. Any number will do. Very long. How much long? Roughly at least 1,000 seconds or more. Okay. 1,000 second is how much? Is 33 minutes. Not 33 minutes. 17 minutes. Around 16, 17 minutes. Okay. Not considering time for loading RAM with data. Okay. Okay. So Rohit, trust me, the biggest time it would take is to load the data into RAM as compared to that. So 20 minutes is the answer from Arun. Okay. Sure, sure. So what are your no Deepthi, keep asking your question. Okay. I would love to answer. Did I miss your question by the way? Anywhere? Oh wow. So Mahesh says that it's 5 hours. Okay. Yes. So basically, it took me 5 hours, and I also could not compute how much time it would take actually. Okay. My gut feeling was saying that it would take probably around 1 hour, and but it took around 5 hours to sort this data, and that too on a solid state hard drive. Remember that part. I did it basically using multiple solid state hard drives. I did a 1 terabyte journey. Okay. So what I wanted to tell you is that 5 hours is too many hours to solve this problem. So far, yes, yes. Mahesh is right. So far, we always thought that sorting the data is a small thing, right? But it's actually a big thing. It takes long time. And why I'm asking about sorting? Because sorting represents, by and large, the computing in even as the word. Okay. Why does it mean by why do we mean by sorting as computing? Because anything you do with respect to relational databases, say for example, you are creating indexes. Indexing is nothing but sorting the data, right? And when you look for something via where clause, generally it looks up in the indexes. So where clause is a direct reflection of how fast you can sort. Similarly, when you do a group by is a direct reflection of how well can you sort the keys, right? Sort the ID columns, and therefore group by is a sorting problem. Similarly, joins, when you join two tables, you are basically joining two sets. If they are sorted, joining the two sets is very, very easy. And therefore, join also is by and large a sorting problem. So effectively, if we look, most of the problem in the industry or most of the problem in computing can be converted or expressed as sorting problem. And going by the same philosophy, MapReduce is also basically exploits the sorting in the network. That's all. MapReduce basically provides you a sorting, right? So now before going into the details of MapReduce, here we realize that it took lot of time. 5 hours is lot of time to process the data, right? Let me answer Rohit's question. Does something like a graph database require sorting? Yes, even if you do a graph searching, if you look at most of the algorithms, beneath the hood they will require you to sort the data. Okay? So graph databases also require sorting under the hood. Okay. So Deepti's point is she was not able to join from the beginning and she's new to big data. See, everybody is new to big data by and large, most of the people. So nothing to worry on that part. And I'll try to avoid, and I'm trying to avoid most of the keywords which we have learnt in the first half, and some of them used over and over again. I'm trying to avoid it and trying to define again. So do not worry and just I mean do not worry that you missed anything. Okay. All right, so here big data problem, here we are talking about processing, and we took 5 hours. No matter what I did, this was the best time I could come up with, and I can bet nobody else in the industry can go beyond those 5 hours. All right, that's a I mean upper limit. Okay, now 5 hours is not enough. It's we require faster sort, right? And 5 hours is not because my coding was bad, my way of sorting was bad. It was because the hardware was the limitation. The RAM became the small problem, so I had to split the file into small chunks and then load one chunk at a time and then try to sort it. And when I was able to load stuff into RAM, then CPU was the bottleneck. All right. So effectively, we require faster sort, and single computer, 1 terabyte data cannot be sorted very fast, right? Bigger data sorting. What if my data grows from 1 terabyte to 20 terabyte? Okay. It won't be 100 hours. It will be far more than, I mean, the hours will not multiply by 20 if my data is multiplied by 20. It will be far more than that. Okay. And therefore, you need to come up with a better solution. Third one is we might have to require sorting more often than more often than the static data. Okay, and therefore lot of people worked on this sorting problem, worked on the sorting problem. To an extent, there is a sorting benchmark where all these companies, starting with Google, Yahoo, Hadoop, everybody competes in who can sort bigger data and faster, right? And on 8 September 2011, Google published this statistics: 10 petabyte data, which means 10,000 times of our data, 1 terabyte, right? Took them only 6.5 hours, and they used 8,000 computers, right? That is marvelous. And thanks to all these distributed computing, it is fairly possible to to reach to that level. All right. So sorting is ordering the data. Sorting is equivalent to the ordering data, and ordering the data is the basic problem which most of the components try to solve. Okay, except for graph databases. Graph databases utilize this property of sorting and build something else. All right. So now, how does how can we distribute this computing over to multiple computers? How can we use multiple computers to do my problem? That is what is this MapReduce or yarn framework is about. All right. So basically, in this, similar to HDFS cluster, we have got master and we have got slaves. Okay, we have got master and we have got slaves. Master is called job tracker and slaves are called task trackers. Job tracker takes your order. You go to job tracker, it write down your order, and then and your order is in the form, okay, this is my computing and I want to do computing and churning of this data which is located in this particular file. And when I say this particular file, this file is from HDFS. You remember in the previous point we discussed, like in HDFS we have files which are distributed across networks, there are blocks and all those things. Now when we ask job tracker to do something, we give him some task. Okay, and job tracker divides the task amongst multiple task trackers and notes down what he what he gave to any task tracker. Okay, which job was given, what piece of work was given to which task tracker, and once that task tracker finishes, it makes a note that this task tracker has finished. And once all the task trackers have finished, then it updates the status of the job saying job has successfully completed. Now there are few more things. So this is pretty straightforward. Job tracker behaves like a typical manager who take your order, divide it amongst multiple task tracker, get it done through them, and then reply back to you. All right, that's the standard way we have known it. Now there are few more nitty-gritties here and there. First one, whenever you give job tracker a task, you also give optionally a file which you want to churn, right? And remember the file which we have stored on all the data nodes. And generally, data node and task trackers are running on the same computers, and admin node and job tracker is running generally on the similar computer, same computer mostly. All right. So whenever we give the task to job tracker saying that we need to churn this file, okay, now job tracker will do some really smart thing. It will ask admin node, hey, can you tell me on which data node is this file available, where are these blocks available, and based on those blocks it will figure out that which are the task trackers located near to those blocks, near to the file data, the file you are trying to churn. Okay, wherever that file is located, it will send your code to only those task trackers which are existing very close to the data you want to churn. And that is what is the power of job tracker, so that it doesn't have to transmit the data. All it has to do is churn the data, right? Now Other point is that in case one task tracker goes down by any chance, job tracker continuously keeps pinging and asking job task trackers, hey, how are you doing? Hey, how are you doing? In case job task tracker says, hey, I'm dead, or it doesn't respond, it shifts that work to another task tracker immediately. Okay, so that is what the resilience is known as. This is what is resilience in terms of MapReduce or Yarn framework, where even if one machine is dead, still your computing is not stopped. Okay, and all of the computing is sent near to the data instead of bringing data to the code. Okay, all the code is sent to the data. All right, any questions? I have few questions, I'm just waiting. If you don't ask me, then I'll ask myself. So do you have any questions? So we have job trackers, task trackers. Job trackers assign work to task trackers work and then do the computation, and then it responds back to the job tracker saying we are done. Once all the tasks are done, it responds back to the client saying everything is successful, or it just updates the status of the job. Now, job tracker does few smart things like which is called data locality optimization, which means sending the code to closer to the data. All right. So you guys don't have a question at all. Either I'm a great teacher or who could teach everything, or I'm really a dumb teacher who couldn't explain you anything. So it could be either of the two. So did I confuse you guys, or you've just slept off? Okay. Thank you, Rohit. Rohit is saying, good teacher, don't worry, you're doing good. Thank you. And Kumar Swami's question is, how does it decides how many tasks to create? Very good point. Very good point. So generally the decision is based on how many blocks are there for that file. Okay. So whatever file you are trying to churn in this computing, the way we were trying to sort a file of 1 terabyte, so whatever number of blocks are there and how they are distributed in the network, if these 1,000 blocks are distributed on 50 nodes, then what it needs to do is it needs to create 50 task trackers, because 50 computers are having those chunks of files which you need to process. Okay, so that is the prime criteria of dividing the work. All right, okay, good, good. So what if admin node, probably you are talking about job tracker over here. What if job tracker fails? People generally keep a backup of job tracker. Job tracker doesn't contain any data per se, much of a data other than the data queue. Nothing else is maintained by job tracker. So even if job tracker is dead, you can replicate it quite easily. In case admin node fails, then you have backup admin nodes, right? How does it decides the number of blocks? Okay, since the default size is fixed, okay, default size is fixed to 128 MB. Therefore, number of blocks are just total size of your file divided by 128 MB, okay, plus a remaining one. Okay, so that is how it is designed. That is how the number of blocks is decided. Now you can answer me, if you have 128 MB file and you got say you got 600, sorry, you got 128 MB of each block size, and you are trying to store how much? Say you are trying to store 600 MB. How many files, how many blocks do you think it will create? 5 blocks, right? It won't be 5 plus, it will be 5. Okay, it will be 4 plus, right? Now, all right. So Kumar Swami's point is, what if it is not a file? What if it is a process? So see, process is okay, right? Process doesn't matter. Here we're talking about the file. So process you don't store in the right away in the file system. It is loaded into the memory. So actually, I could not understand Kumar Swami's question. So could you just repeat the question? It'll be great. I'll try my best to. All right. So I have answered hopefully Manikandan's question. Who is going to create this architecture? Will this not alter any task problem? Mean number of admin node, data node change based on the requirements. Right, right. So number of admin nodes and data nodes change based on the requirements. Okay, based on the requirements. A new node is added to the cluster, data will be redistributed, as well as task trackers will be running more. And if you have got more hardware, you can add them quickly at any moment of time and data will be redistributed. All right. Always the admin node will remain singular while data nodes will keep on changing as per the requirements. All right, Arun? Okay. So now, Money, yeah, I forgot to mention that, yeah, you are right, Money. Money is saying that what about the backup copy? We said we will store 600 MB on 5 nodes. And what about the backup copy? Okay. So backup copy will generally go to the other nodes. All right. And therefore, it might take maybe um, few more nodes. All right. Few more nodes here. Okay. Okay. So Kumar Swami's point is very valid. Swami's point is very, very, very valid. He says that whose job is to divide the work among task tracker. You have got certain process. You have got say you have to group by the data. Now, how will it divide the data? Divide your logic such that it will run without any problems. Who will divide, right? Because not all programming problems can be divided into multiple machines. That's where the MapReduce kind of phenomena comes into picture. MapReduce is a nice paradigm where you try to convert all your problems into key value pairs. Okay, all your problems into sorting data. Okay, so MapReduce is nothing but a grand sorter, grand grand sorting algorithm which uses so many task trackers to sort the data. Okay, and sorting is fairly parallelized process, which means each chunk is parallelized and sent to different computers, and that each chunk is sorted and then sent back for merging on a central node. Okay. Now Arun's other question is, admin node remains constant, data node changes. Yes, you are right. Any other questions here? So the same process has been described in these diagrams. Okay, where, right? So where client goes to the job tracker, then job tracker asks all the task trackers to perform various tasks and let them finish it and update the job tracker. Job tracker then, once all of the tasks are finished, it sends back to the information. Okay, so dash dash means client submitted the dash dash job, and this means the map reduce jobs are happening on all machines. Okay, so map reduce is basically a grand sorting algorithm. On top of it, we write two kind of functions called map and reduces. Map is run before the sorting starts. Maps map is your code or logic whose duty is to define the key for the data so that MapReduce can sort your data based on that key. And once it is sorted, then whole of the data, whatever comes in for one particular key, is passed through something called a reduce. Okay, so it's a grand group by statement. Group by this key and then a- apply this aggregate function. So aggregate function is your reduce functions with whatever you like to write, and group by statement is equivalent to defining the key for your sorting. All right. So MapReduce is the most easily parallelizable task out of all kind of paradigms. All right, so this is the same thing which I explained in other diagrams, where the job tracker also keeps on sending something called a heartbeat to all task trackers, and so that it knows the health of all the task trackers, and in case the in case any of the task trackers dies, it will send the job to any other task tracker which is near to that particular data. Okay, is everybody with me? All right. Awesome. Awesome. So here we go. Now we have got, so this was the job tracker where it divides the work and sends to all machines. And how does MapReduce divides its works? Okay. MapReduce divides its work in this manner. Say you have got three blocks, split 0, split 1, split 2. These are the blocks staying on different three computers. Whatever you write as a map function will be applied on each of this file or each of this split, and map will create an output which will be having a key and value. So map is your logic, how you define your key is up to you. Okay, and whatever output comes from map, you the map reduce, the task tracker will sort it. Okay, the task tracker's duty is to sort it. Task tracker ran map function which you defined on each data node section. This is lying on the data node. Whatever data was there, map was applied on that data. And that data, whatever map, your function generated key value pairs, that task tracker sorted this data. Okay, sorted this data, and once that sorting finished, it is merged back onto a central machine, and then the reduces are applied. Reduce is your function which tells what to do with the values, all values for a particular key. For each key, what you need to do, that is the role of the reduce function. So once sorting merging finishes, then the reduce is applied. Even if you do not understand map reduce right now, do not worry at all. Okay, do not worry at all. We go through map reduce exercises more and more into details into 3 more sessions. Okay, so that you start thinking in terms of map reduce when we give you a challenge. Okay, now these are the other components in the Hadoop ecosystem. So first one is, we talked about file system. We talked about the compute engine, which is Yarn and MapReduce. Yarn is the resource manager who divides the tasks, and MapReduce is the paradigm which runs mappers and reducers on various machines and does the sorting. While there is something called HBase. HBase is used when you have billions of rows and millions of columns. In those cases, you use a database called HBase. And HBase stores its file or data onto HDFS. So HBase stores its data onto HDFS, and HBase is basically for huge tables, huge tables. Okay, and you can run MapReduce on top of HBase as well as HDFS. When HBase as in, whenever we run MapReduce function, we always define that this is my input file, and in case you are running your MapReduce again HBase, you define that this is my input table. Okay, so MapReduce remains as the core computing logic in the whole game mostly. Even inside Spark, there are maps and reduces similar to our map and reduce. Okay, paradigm is similar. Now, Hive is now every time you have to do some computation, you cannot keep on writing MapReduce functions all the time, right? It's too time consuming. It's a repetitive, and you will keep on writing same code again and again, as well as you need to be proficient in the programming. So lot of people worked on it, and someone came up with a SQL interface. You write your query for the data which is lying on HDFS or in HBase. You write your query, and Hive will convert the map reduce under the hood for you, okay, and run it, right? So you do not have to think in terms of map reduce when you are using Hive. All you have to think about, where is my data and how do I what query do I write. So Hive is exactly a SQL interface for Hadoop. All right, and that's like a very brilliant thing with which was done. Now, after a point of time, people realized that SQL is not sufficient when querying the data from querying the big data. Therefore, they coined a newer language called Pig Latin. It's a very beautiful language. I like it more than SQL, though I am a big fan of SQL. So, Pig Latin is a language which is designed specifically for big data querying, and it's a very simple language. It's far more simpler than SQL. Because in SQL you have to write everything in a single query, join this, join that, combine this, filter this, everything in a single query. In case of Pig Latin, you can write it as part of multiple queries. That is a beautiful thing which was done by Pig. Now next thing is Mahat. Mahat is a machine learning library or machine learning algorithm library. So we talked about sentiment analysis, we talked about clustering, we talked about recommendation engine. Those will look scary, right, in the first shot. But the beautiful part is Mahat has got a, a very simplified interface to generate recommendation, to generate clustering, to generate lot of machine learning algorithms are available as part of this Mahat library. As well as there are other libraries like GraphLab and all, which we are not covering right now. Okay, so Mahat is basically a very great thing which was done. Why? Because people don't have to be data scientists to be able to generate recommendation. If a usual developer should be able to do all of this without knowing all the statistics, and that was the role played by Mahat. It is just a collection of algorithm which you can use anytime in, whether from the command line, from the another program, or directly. All right, so that is Mahat. So Mr. Kumar is saying that, but do you need data in table format for Hive? No, we don't need the data in the table format. Okay, You can churn the data using Hive even if is in the CSV format and lying in the HDFS as a plain vanilla CSV format or tab separate values. So all of this can be very beautifully done using Hive. Yes. On the other note, it is basically in a tabular format. When I'm saying CSV or tab separated values, it's actually in tabular format. So your point is actually valid, but it not necessarily need to be a database table. All right. Anybody else has question? Very good point. Hello, Kumar. Anybody else has question? So can NoSQL database be used alongside MapReduce? Yes. So on one of my YouTube channels, I have hosted a video which shows that how to use NoSQL database such as MongoDB along the side of MapReduce. Okay, you should go through that video. Okay, any other questions? Feel free to ask. All right, so this is the work, the system, and then you have these unstructured data import and export, which is Flume and Scoop. These are the two tools. We will give a demonstration on how to use these two tools in during the sessions. Okay, so if you have lot of Apache logs, lot of photos, videos, you want to upload them into HDFS, you can use Flume. Flume will launch in a parallel method. Flume internally also uses MapReduce such that it can load the data parallelly using multiple computers directly. Okay, so similar is the case of Scoop. Scoop is great for loading the data from the relational databases. Okay, onto HDFS. These are like a ETL solution for you. ETL is extract, transform, and load. They are not as great as Informatica, but these are good solutions, good enough solutions. All right. Now, when you are building any of your big data solutions, right? Your some commands will be unstructured data, some commands will be structured data, on top of structured data. Some will be, say, you are doing something on HBase. Some would be you ran some part of it into as a Hive query. So your whole solution will be built using all these components. So you imported your data using Scoop, then you ran your MapReduce job, then you hand it over to Hive where you ran a query, and then you ran your Mahout algorithm on top of the fine cleaned data. This is exactly what we were doing at most of the places in past. Now, overall objective generally remains that we run some Mahout algorithm like recommendation or clustering or those kind of algorithm, right? Now, how do you stitch them together? Okay, that is the job of Uzi. To Uzi, just like we do it with the ant. Okay, just like we do it with the ant, we tell that do that. All of that kind of workflow is possible using Uzi. So Uzi also we will cover in our sessions. All right, now this is the whole ecosystem we'll be covering, plus few more tools such as Zookeeper will be covering those aspects also. We'll covering Spark, we'll covering MapReduce, we'll covering Yarn, we'll also cover Storm over here. Okay, Storm also and Zookeeper, right? And this is the complete ecosystem which will make you powerful enough to build your big data solutions. Okay, all right. So Hello's question is, how is it different from SAP HANA Hadoop as big data solution? So SAP HANA is just one small solution. Okay. Here we are talking about a file system, a database, a import export tool, and and MapReduce engine, Spark, Hive query language, Pig Latin, Mahat. SAP HANA is in-memory database. SAP HANA is an in-memory database. Okay, and along with the in-memory database, it comes with an appliance also, which means there's a huge computer which comes up with something like 200 GB RAM, and that's what it does. So you cannot right away compare SAP HANA with any of these tools because SAP HANA has got different objectives. SAP HANA is for little smaller database, but for the requirement where you have, you know, very fast turnaround time you require when you have to process lot of data, uh, GBs of data at a very fast pace. In those cases, SAP HANA is great. All right, right. So Rohit is supporting my point. So he says that HANA is used where real-time analytics can be required. Although there are multiple solutions which can be used for real-time analytics, even like Spark streaming is fairly real-time, as well as Storm is fairly real-time. All right. So this is the whole ecosystem which we will be covering, and I hope that you understood the role of each of these. Is there any doubt which does what? We have import export tools into the file system, and then we have compute engines, MapReduce, Spark, and say Giraffe, and we have HBase. Then we will have Zookeepers, then Hive, then Piglet, and then Mahat. Okay. All right. Should we move on? All right. So I'm assuming that you all understood it. So, okay. Mahesh, you have raised the hand. Are you okay? Or you have a question? All right. All right. Now, moving on. So, this was pretty much from our side on Hadoop. So, those who are part of our sessions and attending, they can go to Ambari and then access our cloud labs. You can see it looks like this. So this is a Ambari is our admin console using which we manage whole cluster. Okay. In case you are planning to set up your own cluster, Ambari is better, slightly better than Cloudera's setup. Okay. And for some reason, right now my network is slow. All right. Here you can directly interact with HDFS. So this is our HDFS. You can see that there are folders here. You can see these folders. There are files. All of these files are sitting in a Hadoop cluster, HDFS. Okay. Now, as you can see that we have got some amount of storage, some amount of monitoring capabilities, and all of that. Okay. So basically, this is running on a cluster. Great. And all of the students have created their own folders and they are using those. And so this is the interface where you upload your files and you try to access the cluster from the browser. And also you can create a Uzi job from here itself when you are stitching it. To run pig hive queries, you can run from here. This is hive query interface. That was pig, and this is hive query interface. So the other thing is you can directly SSH onto our servers and then start working. You can directly SSH and then start working. Right? So setup document is available in our LMS. Those who are part of our sessions, they can access directly, and also finish the questions based on all the assignments based on today's session. Okay, this is for the candidates who have signed up for the full course. All right. For more detail, you can look at this Wikipedia URL as well as the design document of HDFS. Those are the very good ones. And in case you want to sign up for the full course, we have got 4 seats available as of today. Okay. The rest of the seats are full in our session. Only 4 are left. So in case you are interested, you can sign up for 8th November course. The class will start at 8:30 p.m. and end at 11:30. There will be 11 classes in total, and each class will be similar to today's class, 3 hours class. And this is 14,995 is the total fees, including everything. All right. So any questions do you have? So cost is 14,995 including everything. All right. So feel free to drop by, and if you have any questions, feel free to ask, and I would love to answer all your questions. Okay. So that's pretty much from my side. Stay connected. Even if you are not attending the sessions, stay connected. Maybe something works out. And yes, you'll get a certificate. And we get generally basically we give a permanent URL, and this certificate is crawlable, which means that when people are searching for your name, there are chances that they will bump into your certificate. Okay, and it will be displayable on. You can display it on the LinkedIn, and you can put it anywhere. Okay, and also we'll retain this certificate so that the people can come and you know join us, right? Also, we would like to have your link once the course finishes. We'll request your LinkedIn profile link so that in case a recruiter is coming and you are interested, we will just tell them that this is the LinkedIn profile. You talk to the person. All right. So that's the kind of certificate we provide. That's the kind of certificate we provide. Any questions you have for me? All right. So thank you very much for the session, and how the players like Google and Yahoo were playing with big data and Hadoop, big data before Hadoop. So that's a very good point. So from the beginning itself, Google built some sort of distributed mechanisms. Okay. And all of this, like I was telling you before Hadoop time, right? At Deisha, we had built our own small niche solution. For each problems, we had to build custom algorithm which will distribute the data and distribute the logic as per our choice. Okay, and that used to be really tough time. And because of these tools only, this era has actually taken a pace. Okay, had these tools not been very popular, then probably we wouldn't be discussing this. Okay, had not these not been very open. So hope I answered your question, Kumar Swami. So Mahesh's point is, am I offering any offline classes? No, actually, because we stopped our offline classes because our offline, the people who attended our offline classes, their performance was not great. And same people when they attended the online classes, their performance was tremendously changed. So we realized that our online classes are far more effective than our offline classes. So we stopped the offline classes completely. Okay. Okay, Rohit. So thank you. You also got to know each, I mean, lot. I got a great questions from you, and thank you. So Mahesh, actually, we have. I mean, what we do is we do everything online, and it's actually pretty good. It's actually pretty good. The performance of all our candidates is far better than any offline candidate. Okay, so you don't have to worry about that. Okay, so Kumar Swami's point is, but they were still big and fast enough. Right. But no, actually, those solutions were not really fast enough. The file system like HDFS is like a wonderful solution. Okay, we never had such a solution earlier. The solution which I gave you, right, folders and there are network drives we mounted, that's the kind of thing we had built, okay, before Hadoop kind of solution. Those were not that sophisticated. So Anand, again, Anand, his question is same. Is there any classroom training for full course? No, we have stopped the classroom training. The other reason for classroom training is you will never get a good instructor in classroom. Okay, therefore it does not make much of a sense. Those who really are committed to good training, they are all doing online. Reason being that the experts may not be available in your city, may not be available in your location. So Arun's point is that okay. So this certificate is not meant for you. This certificate is meant for other candidates. So you don't have to do that. And okay, online classes only on weekend is possible. Yes, Mahesh. Right now only on weekend because we are targeting the individuals who are working somewhere. Therefore, giving a training only on weekend works out for them. So, yes, Arun, we will send you the soft copy of this presentation along with the video of this presentation. Okay. Anand, Anand, was I able to answer your question? Yes, Amjad, you will get the video recording of the session. Yes. So you can reach me. You have my phone number. You can see my phone number in this slide. Okay. You can reach me directly. All right, Mahesh. We will teach you how to configure Hadoop in one of the sessions, Anand. Nothing to worry. But for time being, if you are very enthusiastic, have a look at Ambari. Using Ambari, you can instantaneously set up your Hadoop. If you are planning for a single computer, you can download a virtual machine from Hortonworks or Cloudera, and you can get it running within couple of hours. All right. Alright. So I will send you these sessions recordings as soon as I'm able to upload them. I'll send it. And alright. So I hope you all like the session and feel free to blog about it, write about it. Okay, whatever you prefer to do. And stay connected even if you're not going ahead with sessions. stay connected. And if you have any questions, just drop me an email, and I would love to answer your question. All right, great. So have a good night, and connect with me tomorrow morning if you have any questions. All right, bye bye, and have a great day. Bye, Kumar Swami. Bye, Swapnil Vats. Bye, Deepu. Bye, Mahesh. Bye, Amjad. Bye, Manikandan. Thank you, Mahesh. Good night. Now I'll just disconnect it. Good night, guys. Have a great day tomorrow.